Hello, my name is Angel Rubio. I'm an industrial engineering student at the University of Texas at Arlington. My machine learning project for this junior semester is on predicting water consumption for better resource management. Access to clean water is something that to many people in the world is unfortunately a luxury that can't be afforded. In many developing regions, even when water is available, access to it is limited, and this can put severe strain on communities in the area. So this project aims to optimize water delivery operations by predicting a customer's reorder frequency and amount. And by being able to predict this, we can alleviate some of the strain. So in the Jacala, Chapulhuacan region of Hidalgo, Mexico, where my family is from, there has been a problem with developing access to water. The nearby Amahac River, which was usually used as the main source of water for the people in the area, has lately been drying up and been polluted. There has been limited assistance provided by the government as towns are hard to travel to because it's a mountainous region, and now there has been an uptick in demand from private water sources. My family actually operates a small private water delivery business in the area, but to be able to address this demand, they would like to know more about how often their customers will need to reorder. And here, this picture is the Amahak River, which is previously it was one of the main water sources for the people in the area, but lately it's been getting there's been landfills in the area. It's been getting polluted. This is just another picture showing a town where my family's from. It's called Jacalilla in the region, and it's just to show how difficult it can be to actually get to these houses where the water is needed. In this picture, you can see storage tanks on the roofs of a lot of houses in the area. So currently, many homes in the area use rainwater capture and cleaning systems like this, and they use this to supplement their water supply. However, most homes and buildings have a larger tank either somewhere next to the home or underground, and that's what gets refilled, and it's actually their main source of water. So just for a little bit more background, there are a lot of smaller family-owned water delivery businesses in the area, and they often work together and they share customers and information with each other. So most of the deliveries in the area are made with smaller tanker trucks. The one pictured here is actually my uncle's. He gave me a tour last time I went. Um, he uses it to make deliveries to towns up to 4 hours away from where he lives. And that's actually not that far because the roads are they're winding down the mountain and it's not that much distance to travel to, but it takes a long time in that specific vehicle, especially when it's loaded. Most of the households use about 4,000 gallons a month, and the capacity of these trucks is about 3,500 to 4,500 gallons. So one delivery to a house can hold up to about a month of the household's water. And sometimes they use one full truck to supplement a lot of homes' tanks. Originally when proposing the project, I planned to use electricity, propane, other fuels, and water order data and consumption data to model the water reorder prediction. However, I scrapped this idea as other fuels and other resources, they have different usage rates and they're not a one-to-one comparison to water consumption. They have different needs, they have different transportation requirements. They wouldn't model exactly to what I need to be able to predict water consumption rates here. So I decided that the data used for this model should only contain water consumption data and it should be recorded in rural areas for a more similar result. So I selected the 2023 water use in Texas dataset as it contained information from a large variety of towns in Texas, and a lot of them had similar living and water conditions to the region that I'm studying in Hidalgo. So I obtained this dataset from the Texas Municipal League, and the Texas Municipal League is a group of Texas cities that come together and share data. They share different interests of towns in Texas, and they get together to see what they can improve together. So the data set is split into 8 columns, and it's an accumulation of the population data, customer data, and usage and fees of various participating cities in the state. My study to predict the water usage of customers was done by applying decision trees, the random forest algorithm, and k-nearest neighbor algorithm to forecast household water requirements and suggest improvements for future implementation. I also ran linear regression to see how well it would fit the model. However, this wasn't the main goal of the project, and I did it more just for a comparison of the other 3 models. I chose the best model based off of how effective it is at predicting by selecting the model with the lowest error, and I also took into account the ease of use, as I wouldn't be the only person running the experiment, and I would like to make it very easy for people who aren't familiar with the system to be able to apply this. So the decision tree applied to the dataset, it determines the average error from the actual average value found in every splitting node. So the trees were very large and difficult to read visually, and it's the one that's actually pictured here. This was the same result I got after running it. All the experiments made use of all the available columns of the dataset, accounting for population to the average fees paid per gallon usage up to 20,000 gallons. So the single decision tree was run about 10 times. I did this to ensure that everything was processed correctly and that every single run of the decision tree was consistent. I applied the random forest algorithm as a more refined version of the decision tree. However, when I was trying to process the random forest, the time needed shot up from about a few seconds to about 15 minutes. Because of this, I only ran the random forest on the dataset about 5 times, just to ensure consistency and results were all the same. And the output it gave me was, I limited it to only about 10 decision trees for the visual. However, it gave me a lot more. For my KNN algorithm, I actually initially ran it with the decision trees because I noticed that the random forest would shoot up the time. So to keep it concise, I ran the KNN with the decision tree. The KNN algorithm for this dataset used the K values 3, 5, 7, 9, and 11, and I used 10 folds for cross-validation. I used cross-validation because I wanted to provide a more reliable estimate, as my dataset was on the smaller side, and if it wasn't included in the code, the results would really stray from the actual average prediction value. So I ran the KNN code about 10 times, just like the decision tree, just to keep processing time down, and just to ensure that everything was processed correctly and that every run was consistent. I ran linear regression as a comparison to the 3 models, but it was just for, essentially just for fun, just to compare the results. After this, I decided to choose the best model just based on the lowest mean average error value and ease of use for the end users of the project. So in the visual, you can see I plotted the results of all 3 different methods, and the line you see down the middle is the actual average value predicted. So that's why it's constant. The random forest algorithm was decisively the closest to predicting water usage accurately, as it had the lowest average error in every run it was tested in. The KNN results, however, they were surprisingly remarkably close to the random forest results. And in every run, all 5 of them, which they were compared, uh, the KNN was only off by about 4 gallons in comparison to the random forest. The basic decision tree results, they were consistently hovering around the 1,000 gallon mark, and they had significantly higher error than both the random forest and the KNN. The linear regression ended up not being perfectly accurate for the process, and it had a much larger error. Um, it was initially used in a previous course. I wrote it in R and I just adapted it in Python for this project. The lowest error of the random forest and the KNN were about 750 gallons, and this is about equivalent to 5.6 days of water usage in an average household. This was expected as water usage. It can vary on many factors like season, just how much you're limiting yourself to using water. It could be anywhere from washing dishes to watering your crops, because that's something, there's a lot of subsistence farmers in the area, and that can also affect it. Um, However, the finding was consistent on every single run of the models. Further improvements on the accuracy of the predictions, I would like to implement a data recording process based on customer order information over the summer. In doing so, I think there would be a higher quality, or the results would be higher quality data that is directly linked to the area instead of depending on demographic similarities that ignore the scarcity of water and the habits of the people in the community. As the methods applied in this study were kind of rudimentary, the topic would greatly benefit from the application of more complex models for predictions, for example, applying neural networks to the problem. I plan to improve the methods and data, and once considerable accuracy has been achieved, I would like to present my findings to the municipal government and hopefully help improve the quality of life of thousands of people in the region. Thank you for taking your time to watch my presentation, and thank you to my professors for teaching me the methods that I used in this project. If you have any questions or have any suggestions that I could apply to this in the future, please contact me at the email you see on the slide or message me on the LinkedIn on the link provided. Thank you very much.